Many modern detergents don't contain only the ionic sulfonate ions, but also a whole range of other substances whose purpose is to assist the detergent in its cleaning action. One such substance is tripolyphosphate ions. Now, as the name suggests, tripolyphosphates, their structure is related to that of a phosphate ion. The fact that we've got the tripoly at the start means, so poly means many phosphate ions, and tri is going to tell us that, well, that many is actually 3. So before we look at the structure of a tripolyphosphate, it's really important that you are familiar with the phosphate ion, which you should be. So you'll recall that the formula for the phosphate ion is PO4 with a 3- charge. And basically our tripolyphosphates are arrangements where we have 3 of these tetrahedral phosphate ions joined together. Now there's 2 different forms of tripolyphosphates that we're going to look at. There's the cyclic tripolyphosphate, where our 3 phosphate ions are joined together to form a ring, or there's the linear tripolyphosphate, where our phosphate ions are joined together to form a chain. Now, it's important that you can draw both of these structures correctly. Also, once you've drawn the structure, you can always count up and see what the formula of the ion should be if you've forgotten what the exact formula is. Now, the process in which you use to draw it can assist in making sure you get a nice, neat diagram. So if we have a look at the cyclic tripolyphosphate, basically we want to draw a 6-membered ring in which the vertices are alternating phosphate and oxygen atoms. So we would go phosphorus and oxygen. Phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen. So that gives us the basis of our structure. Now, around each of these phosphorus atoms, it is a tetrahedral arrangement. So it has the same arrangement of atoms as we've got in our individual phosphate ion. So basically the next thing we want to add is a double bond to an oxygen on each phosphorus. And then we can see that each phosphorus has a double bond oxygen and 2 single bonded oxygens. We'll notice over here that it needs 3 single bonded oxygens, so we just add a single bond oxygen to each of those phosphorus. Now, the other really important thing to take note of with drawing your structures is that oxygen should always have 2 bonds coming off of it. So either in the form we've got at the top here as a double bond, or what we've got over the side here as 2 single bonds. If it's only got 1 bond, you need to add a negative charge, such as that. So there's our cyclic tripolyphosphate. Now if we count up what atoms we've got there, we can see we've got 3 phosphorus. We look at our oxygens, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And for our charge, we just count up our negative charges. We've got 3 of them, so it's 3 minus. So the formula for the cyclic tripolyphosphate ion is P3O9 3 minus. Let's now have a look at the linear tripolyphosphate ion. Now in this case, we have a linear or a straight structure. So what we want to draw is a chain of alternating phosphorus and oxygen atoms. So basically, we start with our oxygen, go up to a phosphorus, down to an oxygen, and we continue that until we've got 3 phosphorus. Okay, so the next thing we want to do is add our double bond to the oxygen on each phosphorus. And then we'll recall we need 3 oxygens single bonded to each phosphorus. We've currently got 2, so for each one, we're just going to add 1 in the middle there. Now those ones that we've just added only have one bond, therefore they have a single charge. We'll also notice that these ones on the end only have one bond, so we'll add a single charge to them as well. So this time if we count up what we've got there, we can see we've got 3 phosphorus, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygens, and we've got 5 negative charges. So the formula for a linear tripolyphosphate ion is P3O10 5-. It's important that you practice drawing these structures so that you're confident. You can always scribble them down and work out your formula if you need, and that you are familiar with the structure of each of those ions. Now, as stated earlier, substances such as tripolyphosphates are added to help detergents in their cleaning action. So they need to do something which makes it easier for the detergent to actually perform its function, which is to dissolve in grease or oils to form micelles, which can then get washed away. So there's 3 main ways in which tripolyphosphates assist in this process. The first is that they produce slightly alkaline conditions, and they do that via the following process. So you can see that the tripolyphosphate ion has acted as a base, and it has accepted a hydrogen from the water molecule, which has left us with a hydroxide ion, which is why it has produced slightly alkaline conditions. Now, the reason that is favourable is that it ensures the detergent anions remain in ionic form. So if the conditions are acidic, then those anions could accept the hydrogen ions and be converted into a non-ionic form. And as the ionic head on a detergent molecule, a detergent ion is very important for its cleaning action, so the function it performs, because that's what allows it to interact with the water and therefore be washed away. If this occurs, if the hydrogen bonds to that, giving us a non-ionic product, the detergent therefore can't perform its cleaning function. Tripolyphosphates also act as sequestering agents. This means that they remove metal ions such as calcium and magnesium from hard water, and they do this via the following process. So you'll see here that the metal ion is taken in by the tripolyphosphate ion to form a complex ion over here. Notice that we had a tripolyphosphate with a -5 charge. It's taking in the metal with a +2 charge, and we're ending up with a complex ion over here with a -3 charge. So basically, if the metal ions are taken into this complex ion formed with the tripolyphosphate, it's going to lower the concentration of free calcium or magnesium ions within the solution. What that means is there are fewer of those ions to come into contact with the detergent ions. Again, if the detergent ions come into contact with those cations, they will form non-ionic compounds. Now, in that situation, that detergent anion then can't go on to perform its cleaning function. So it says if there's a lower concentration of these metal ions, more of the detergent ions are going to be free to perform their cleaning function. Lastly, they act as deflocculants. So before you get your head around what a deflocculant is, basically a flocculant is something that causes small particles to clump together and form flocks. So a deflocculant is something that prevents small particles from clumping together. So in acting as a deflocculant, the tripolyphosphates keep small clay particles suspended in solution rather than clumping together and settling back on the surface of clothes. So tripolyphosphates are useful in assisting the cleaning action of detergent anions. However, there are some problems that they can contribute to. One being that they contain phosphorus, which is a nutrient for plants, and the waste water can find its way back into natural water bodies. When this happens, the excess phosphorus or phosphates act as a nutrient or a fertilizer for algae. And this excess of nutrients and subsequent increase in growth of algae can cause the problem of eutrophication.